So what we did on Friday was we looked at calculating work using a very specific method. And that method is that work equals force times displacement. Force is a vector, displacement is a vector, but even though we might use directions in this formula, for example, the displacement might be positive and the force might be negative, giving us a negative amount of work. Even though we might use directions in the formula, work is not a vector. Work, which is a transfer of energy, is a scalar. On your formula sheet, they have FD cos theta. They have even more than that on your formula sheet because they have the full-blown vector symbols. I don't particularly care for that. I think it's just maybe too much. Force times the displacement times the cosine of theta. And if you remember from Friday, I don't even particularly like the cosine theta. The force and the displacement have to be along the same line. So the force that you put in has to be the force in the direction of motion or in the direction opposite to the motion. And all that means is you might have to find a component of the force in that particular direction, in which case you use trigonometry. That's it in a nutshell. We did kind of end the lesson by talking about the fact that since work is change in energy or transfer of energy, you might be able to find answers to problems using a little maneuver around the force and displacement thing. But we're going to focus more on that today. We didn't get the lesson done, so I believe I said 1 through 7 kind of thing. Can you take a look at your work, please, and see if you have any questions you would like me to go over from that group of problems? Go ahead, Nate. Number 3. So you have a 2.20 Newton object that's held a particular distance above the floor for 10 seconds. How much work is done? First of all, that 2.2 newtons is the weight of the object. When I say 2.20 newtons, I'm telling you the force of gravity acting on it. And not that it really matters. I could answer this question very quickly, but I want to get into a little more detail. Not that it's really crucial, but if this is the object, whatever, it might be a book or a box. Pretty small book. It's only 2.2 newtons, so it's like about 200 grams. It's a little paperback book. Since there's a force of gravity acting on it that is equal to 2.2 newtons downwards, and since I'm holding that object at a constant height of, wow, look at that, 2.2 meters. That's a total fluke. I don't know why I typed that. But since you're holding it at a particular height, that must mean that the applied force upward, is 2.2 newtons. And I made a big deal on Friday of mentioning to you that in this formula, work equals force times displacement, that this is the applied force. Right? There are a couple of ways we could explain why the amount of work done here is 0. One of them is that the displacement of the object is 0. The fact that you're given a distance doesn't mean that's the displacement. You're holding it at a fixed position, so it undergoes no displacement. And maybe that's the best way to explain it, is since there's no displacement, there's no work to the object. You are definitely doing work to the muscle tissue, and you're doing work to the moving parts of your body, like your heart is going to beat faster, but you're not doing work to the object. Does that make sense? Even if we move the object this way, this is not a force, I'm just saying we move it 7 meters to the right. Since the displacement of the object is to the right and the force is towards the ceiling, none of that force is in the same direction, which means there's no work. Is that okay? Yep. All right. Other questions? Go ahead. 4? Okay. Let's take a look at 4. So we have a 10 kilogram object that is accelerated from rest to a velocity of 11 meters per second by some horizontal force. There's no friction. Okay, so if there's no friction, what that means is that the force applied to it to accelerate it is the net force. Okay, if I draw all of the forces acting on this object, yes, there is a force of gravity, but is balanced by a normal force in the opposite direction. So these two forces are equal. This is the force due to gravity. This is the normal force. And let's just say that you're pulling it to the right by attaching a rope to it. There's some force here. I don't know if I've drawn these to scale or not, but this is the applied force. And in order for you to find work, you have to take the applied force times the distance. And my point is, how do we find the applied force? We find it by saying to ourselves that this is the net force, which is ma. So we have some kinematic work to do here to find the acceleration. Once we find the acceleration, we can multiply by the mass to get the net force. Then we can multiply by the displacement to get the work done. What do we know kinematically speaking? Let's see. We have VI is 0. VF is 11. The time is 5 seconds. These are meters per second, seconds. We know from the very first unit, and you've been getting more practice as time goes on, we know from the first unit that if you have 3 kinematics descriptors, you can find any fourth. So we're after the acceleration. In this case, it's going to be acceleration equals VF minus VI over t. I don't think I need to write that down. It'll be 11 minus 0 over 5. Can you work that out to get 2.2? Boy, that 2.2 is making its appearance everywhere today. 2.2 meters per second squared. Okay. So we get an acceleration of 2.2 meters per second squared. We can find the net force now, the magnitude of the net force, by taking the mass, which was 10 kilograms, multiplying by the 2.2 meters per second squared, gives us 22 newtons. Now I can calculate the work. Work equals the applied force of 22 newtons. I've already written down the formula, times the distance. Oh man, we don't know the distance, do we? I don't think we were told the distance. So we're going to have to use a formula to find the distance. The nice thing is now, and I'm just going to erase this to tie this all together. The nice thing is now that you know VI, VF, T, and A, you can use any formula you want to find distance, as long as it's one of those 5. So I'm going to use this formula. D equals VF plus VI over 2 times T. And again, the numbers are right in front of us. I don't feel the need to write them down. I'm going to take 11 plus 0 divided by 2 and then multiply by 5. And get 27.5. So you get 27.5 meters. This is D. So now I can take the 22 times the 27.5 meters and get an answer. $605. Zahara, is that okay for you? Okay. In preparation for today's work, I mean, look at this. This was an awful lot of work, wasn't it? I mean, you can ignore the top part of this, but there was a fair amount of work here to solve that problem. Friday, we said work is a transfer of energy. And I made a big deal, I think, of saying, for example, if I do 100 joules of work to a baseball, I give 100 joules of energy to the baseball. Well, if you're asked how much work is done to this object, another way to answer it is to say how much energy is given to the system. It's frictionless, right? We're not pushing this uphill, so we're not adding any gravitational potential energy. What's the only kind of energy that this box gets in question 4? Kinetic. And kinetic energy is 1/2 mv squared. By the way, look at your formula sheet. This is on your formula sheet. Work equals delta E. It's called the work energy theorem. It's actually a formula. But we'll finesse this a little bit more in today's class. There's something else I just don't want to talk about right now with it. But basically, in this case, the work done goes entirely into kinetic energy, which is 1/2 times the mass, which was 10 kilograms, times the speed, which was 11 meters per second, squared. Well, go ahead and run that through your calculator. Take 1/2 times 10 times 11 squared. Gets you the answer in a lot quicker fashion, doesn't it? Now, if there was friction, it gets a lot more complicated. And if it's going uphill and speeding up, it gets a lot more complicated. One final note here. No, I'm not going to do that. Any other questions before we get started today? All right, so we do have one more question to do from Friday, and that's example number 6. So I want to talk about this one, and then we're going to go through the next lesson and get a lot of time today practicing these problems. Well, today and or maybe tomorrow. So the graph shown here is the graph that shows the force in kilonewtons as a function of the distance that a golf ball moves in millimeters while the club is in contact with the ball. And it says determine the work done. Well, work is force times distance, right? Can somebody tell me why, and this is a tricky thing, but why can I not use 4,000 newtons? I'm going to actually write this down. Work equals 4,000 newtons multiplied by, I guess that would be 5 millimeters. Which is 0.005 meters. If I multiply those, what do I get? Can you do me a favor and multiply those and see if you get 4? 2. Or is it 20? Is it 20? Okay, 20. And this would be joules. So why is this wrong? Why is it wrong to do that? I tell you, work equals force times displacement. By the way, the force is in the same direction as the motion of the ball. If you've ever golfed or you think about golfing, that club face hits the ball, and the club face might be moving to your left if you're a right-handed person, and the ball is going to be moving to your left. Why should I not multiply that 4,000 newtons by the 0.005 meters? Aoki? It's okay. That's the exact answer I'm looking for. That force of 4,000 newtons is not the applied force for the whole time. You can't, I mean, imagine that I was pushing a box along the floor and I applied a force of 4,000 newtons to begin with, and then for the next hour I applied a force of 1 newton. You're not going to use 4,000 newtons, right? Okay, so it's clear that you can't use the 4,000 newtons because it's not the force for the whole time. Would you agree that the force of 4,000 newtons happens essentially for the same amount of time as the force of 0 happens for? My question is, what force would you use? An average. An average. So half that force? Let me ask you a question here. And I'm really pushing the limit here. I'm getting you to think very carefully about this. The answer is the average force is correct. Is the average force 2,000? Well, it may or it may not be. Okay, let me give you a different illustration. What if I had a graph that looked like this? And just so I know as I'm explaining this, how many of you are planning on taking calculus next year? Okay, this is mainly for you guys. What if I had a graph that peaked at 4,000 newtons, and it started here and it did this. Or better yet, no, it did this. Do you think the average force is 4,000 newtons? Can you give me a number, Alex, that you think it might be? No right or, well, there's wrong answers here, but give me one of the many right answers. 1,800. Less than half because of all this time it spends over here. Well, in order to use an average, what we do instead, and I'm going to come back to this average thing in a second for you calculus people, is we say that since force times displacement gives you work, the average would be represented by the area of that shape. To how many of you does that just kind of make sense? And that's true in any scientific application. If you have a graph where you have two variables and you multiply those variables together, and that gives you something meaningful, then the area will always be that meaningful thing. So if I had a graph, and I'm getting a little off topic here, but if I had a graph that showed mice per day as a function of days, and it looked like this, then this area equals the number of mice, because mice per day times days gives you mice. One way to kind of explain that is if you could somehow, and this is an analogy I use in my calculus class, put a wall here and a wall on this side as well, and if that graph were a solid chunk of ice and it melted, you'd get a rectangle, wouldn't you? And whatever the height of that rectangle is, that would be an average force. That's where it would average out to be. So our job in questions like this is to find that area. First of all, the lesson here is for this graph, work equals the area. So how do we find this area? What we do is we make a shape that we feel represents that area. Would you agree it's kind of triangular? Anybody want to take a stab on why I don't think the triangle area I've drawn here will be correct? Alex? It's missing, right? Do you believe this will be correct? It's missing some here, but it's got a whole bunch of extra. The idea is you want to try to draw a triangle so that the amount that it's missing is the amount of extra area you have. So maybe it's going to look like that. I might even go a little bit more this way. You are trying to determine, and again, I'm trying to reach some calculus students here. You are trying to determine this area here. That triangular area in red has this extra area, but it's missing this area. So it kind of balances out. What's the area of that triangle? We do have to do a bit of estimation. You have to estimate that. Because the area of a triangle, and I'm going to get rid of all of this, because the area of a triangle is 1/2 base times the height. So you need to know the height of that triangle. I would start putting ticks on here. 1/2 of 4 is 2, so this is 2,000. That means this is 1,000, 2,000, 3,000, 4,000, 5,000 would be about here. I would estimate. So I might say that's 4,600. It's not perfect, but it's an estimate. So area equals 1/2 the base times the height. That means area equals 1/2. The base is 0.005 meters. The height I said was 4,600. I'm going to go 4,700 looking at it again now. .5 times 0.5 times 0.005 times the 4,700. About 11.75. And that would be in joules. So the work done is let's just say 12 joules. This is not a really big deal in this unit, but by the time you get to Physics 30, we'd use this concept of area quite a lot. Any questions with that example? Yeah.
Why wouldn't you just draw like a large triangle, or sorry, a large rectangle, and then subtract the two triangles on either side?
You could. It's not why wouldn't you. I didn't. Why would you? Because it makes sense to you. So what Jay is saying, I'm going to go back to the original diagram. What Jay is saying is he would like to draw a rectangle, if I understand you right, and then take away from that rectangle this triangle. Now, you understand there's got to be some estimation here because of that curve and this triangle. Now that I've drawn it, I will tell you why I wouldn't want to do that. I think there's more calculations involved. Like I would then have to estimate, for example, what this is, what this is, what this is. There would just be more work involved, for me anyway. You could do it any way you want to. You could, what some people choose to do is say, I need that area, so I am going to break it into a series of triangles, which I don't have a lot of estimation with. Like this is pretty much a triangle, right? And maybe this and a rectangle, and then however you want to break it apart into geometric figures that you can calculate the area of is up to you. Usually, though, one triangle is quicker. Any other questions? Okay. So now we're going to get started on today's lesson. which is on page 27 of your unit handout. We're going to spend some time here going over a review from junior high science as well as Science 10, reviewing gravitational potential energy and also reviewing kinetic energy. And then we're going to be solving some problems dealing with those two. So remember from last class that energy is the ability to do work, and work is a transfer of energy. What we're going to be looking at today are different types of energy. And in Physics 30, we use different classifications for energy, okay? But for this course, I'm going to say we're going to break energy into 4 types. The first type is kinetic. And kinetic energy is defined as energy that an object has due to motion. What is energy? It's the ability to do work. Does a moving baseball have ability to do work? Yes. Because if that baseball hits you in the head, it can apply a force to your head, moving your head through a displacement, which is another way to explain that work is done. So, I want you to try to remember that in order to accelerate an object, to give it kinetic energy, it will always require a net force. Net force is what goes into acceleration. Because net force is ma, and a means speeding up, basically. The work done when you accelerate an object with a net force is the energy gained, so it's kinetic energy. Potential energy. Potential energy is energy that an object has kind of hidden. A stick of dynamite has potential energy. Wile E. Coyote's piano that's lifted 10 meters above the canyon floor and being held by a rope. That piano has potential energy. Why? Because if I cut the rope, it can fall and the piano can do work to whatever's on the canyon floor. Why does a stick of dynamite have potential energy? Because if I light the fuse, I can release that energy. A slingshot, a piece of elastic that I pull and stretch, has potential energy. So there's chemical potential energy in the form of a stick of dynamite or a Snickers bar. If I take a safe held above the canyon floor by Wile E. Coyote, that has potential energy, which we call gravitational. A coiled spring. So Wile E. Coyote buys this big spring, he puts his butt in it, and he backs against the canyon wall, compressing the spring, ready to lift his legs so he takes off. That has potential energy as well. It's just called spring potential or elastic potential. 2 grams of radioactive uranium has nuclear potential energy. A battery, before you start using it, has chemical potential energy. One of the points I want to stress here is that potential energy has different forms. Kinetic energy is kinetic energy. Potential energy can be gravitational, electric, it could be magnetic, nuclear, spring, etc. So all of these situations don't really appear to have energy, but under the right circumstances, you can release that energy. Another form of energy is thermal energy or heat. Thermal energy is a special type of kinetic energy. Okay. This is tricky. And I don't need to explain this. We could just go through with the formulas, but I want to explain it. When I throw a baseball from one side of the room to the other, does the baseball have kinetic energy? Yes. Okay. Does every atom in the baseball have kinetic energy? Yes. All right. What happens if I take a baseball and I put it out in the hot sun? It absorbs heat, doesn't it? Well, what that means is every atom and molecule in the baseball starts moving faster. So every molecule and atom in the baseball has more kinetic energy when the baseball's warmer. This is a difficult question to process, but listen very carefully and give it a shot. What's the difference? Here's the baseball. There's the stitching on the baseball. And it's moving this way at 10 meters per second. Every molecule in that baseball has kinetic energy. Here's another baseball sitting on the ground in the sweltering heat. Every molecule in that baseball has kinetic energy. The molecules here have EK. The molecules here have EK. What's the difference? Jay? That's true. So what's the difference in terms of the motion of the molecules in the two balls? And I might even say to you, I would have to do some calculations here, but we don't need to go that far, I suppose, that all of the molecules in this baseball have the same amount of kinetic energy as all of the molecules in the other baseball. What's the difference?
In the heat one, they're vibrating back and forth, so they stay in the same position, where that one, they're all moving towards us.
Right. There's a random, and I'm going to add the word random here, there's a random vibration of the molecules in the baseball sitting on the sweltering pavement. That means that at times some of the molecules are moving in one direction, at times they're moving in opposite directions. Whereas all of the molecules in the baseball, there is still some vibrational energy because it does have heat in it. But for the most part, all of the molecules in the baseball have kinetic energy because they're all moving in the same organized way. They're all moving in the same direction. So when I take two baseballs out from the house and I walk outside, I can add energy to the baseball by throwing it, or I can add energy by heating it up. And in both cases, I'm adding energy to the molecules. So that's what I mean when I say thermal energy is a very special kind of kinetic energy. So when an object is hotter, the individual particles that make up the object move faster. And you don't need to write it down, but you should note they move faster in a random direction. They're not all moving faster in the same direction. This is what happens when you rub your hands together. By the way, if you're like lost in the forest and it's winter, you're not going to be doing yourself a lot of favors by doing this. You're going to be heating up your hands, but you're expending a lot of energy out of your body elsewhere. But what happens is, it's hard to imagine, and I'm preparing you for Physics 30, is you have an atom in your hand with a nucleus, and there are electrons that are in orbit around the nucleus. And electrons are negative. And if I have another nucleus or another atom, next to it, and I start moving these atoms back and forth against each other, the electrons repel from each other. And it's kind of like when you try to drag something with a lot of friction across the floor, it kind of skitters along. What's happening is you're transferring a whole bunch of energy to those atoms, and they're going to be moving faster. The atoms in my hand, when I do this, are springing off of each other, moving faster, creating heat. That's what happens. And one last form of energy, which is light energy or electromagnetic energy. This energy is in the form of light. It's hard to imagine, but light has no substance. There's no mass. It's just pure energy. So light is best described as energy in its pure form. It is not energy associated with any object. It is simply energy. This morning in Physics 30, we were talking about the photoelectric effect, where light hits a metal. And I was telling people that the light is absorbed by the metal. And the question I asked them is, where does the light go? When light is absorbed by a metal, where does the light go? Where is it afterwards? Kai? Right. It's no longer light energy. It turns into a different type of energy, thermal energy. So when light is absorbed, it disappears from the universe. It doesn't exist anymore. What you have instead is, in that case, thermal energy. All right, so let's review now potential energy. The car and its passengers in this ride shown have a mass of 500 kilograms. What is their change in gravitational potential energy when they are lifted through a height of 48 meters? Okay. So I have to admit that you're not going to answer questions like this the same way every time. But as this ride lifts this car of passengers to 48 meters, we're going to assume that it moves at a constant speed. And the reason is this. It's a subtle one, but this is not a simple course at times. If it's accelerating, it's speeding up, which means it's gaining kinetic energy. This question asks about gravitational potential energy. We don't care about any acceleration because that would be kinetic in change in terms of a change in energy. So this is the force due to gravity. This is the applied force. Work done is the change in energy of the car, which in this case is gravitational potential energy. At the top, the car will have energy because if I were to release it and let it go, it could do work on the floor, on anything below it. So the work done here is the potential energy we're after, which will be the force due to gravity. I better not do that. Which will be the applied force times the displacement. Why can I write the force of gravity times the displacement? Jay? Right. These two forces I've drawn are equal in magnitude because it's going at a constant speed. So the applied force is equal in magnitude. And I like that you said in magnitude because they're different forces, right? One's up, one's down. Force due to gravity can be found using mg, so we get mgd. So we take the mass, 500 kilograms, times g, which is 9.81 newtons per kilogram, times d, which was 48 meters. And we're going to get the potential energy because the work done is the change in energy. So you get 235,440 joules. By the way, this whole idea here is why we have this formula, which from now on we're going to use. We don't need to reason out that when you lift an object, the force applied is the force of gravity. We can just say it's potential energy, so we're going to use mgh from here on in. Number two, use the results from the previous example to develop a general formula. Well, I guess I just did, but I will put it up here again. When you lift an object at a constant speed, this is the force due to gravity. And if you're lifting it at a constant speed, then the work you're doing goes into potential energy. You know, another way to look at this is, since the force is against gravity, it's gravitational potential energy. If I took the force pulling on an elastic and used that as force times displacement, then I would get elastic potential energy, the work done. So this becomes Fg This is mass times 9.81, or g in general, which is what we've learned before. And since we're talking about a vertical displacement, let's just use h for height. Again, everybody, what we've just found is a way to calculate potential energy that's gravitational. So here's the formula. The difference is in Science 10, you're probably just given the formula. Here we have to understand how this formula connects to the applied force. And that's a big difference. There it is on your formula sheet. You will notice there's another potential energy formula below it. The one that I've just pointed to is gravitational potential. The other one is something different. We'll get to it later. Toy car is set up on the tabletop. What is the gravitational potential energy of the car relative to the floor? Relative to the floor. Well, gravitational potential energy is mgh. Let's see, the mass is 0.025 kilograms. G is 9.81 newtons per kilogram. H is 2.15 meters. So I get about 0.53 joules. You as well? What is the change in gravitational potential energy when it arrives at the bottom of the hill? Well, there's a couple of ways we could do this. We know that at the top of the hill, we know that the potential energy at the top of the hill was 0.5. I want to get some more decimals here. 0.5272875 joules. Can you calculate for me the potential energy the car would have at the bottom of the hill? So I want you to do an MGH calculation now for the bottom of the hill. Take a look at it. That means that this is H, and you're going to go MGH. Pretty straightforward calculation. I don't think I need to write down any numbers there. We will take the mass, 0.025 times 9.81 times that 0.95 meters, and get that number. So if I look at the change, top to bottom, remember, change in energy is always final minus initial. So we have to take the energy at the bottom and subtract the energy at the top. So let me subtract now the energy that it had at the top, which was 0.5272875, and we get negative 0.232943 joules. That's the change in the potential energy. Anybody want to volunteer why we get a negative? Like, what does the negative tell you about the potential energy? Alex? It loses potential energy. That's a loss in potential energy. Where did it go? Didn't go into thermal energy. This is not like light hitting a piece of metal.
It wasn't actually energy yet, since it would only become kinetic once it actually starts moving.
Yeah, it became kinetic. It wasn't moving to begin with. If it fell from rest or rolled from rest, that would mean it gained that amount of kinetic energy. But I want you to notice something, and we're allowed to do this with potential energy only. In A, it said, what is the potential energy it has relative to the floor? What if it said relative to the tabletop? What height would you use?
2.15 minus 0.95.
Right, you'd use the difference. Can you work that out for me, please? I want to say 1.2. Yeah? So you would use 1.2 meters. And if I said that, how much potential energy does it have at the bottom of this ramp? Nothing, because it's at the bottom. So then you could just do one calculation. Go ahead and calculate mgh with that 1.2. You get the same number. In other words, for this question, everybody, rather than going mgh at the bottom minus mgh at the top, you can factor the mg out and just write mg delta h. Take the height at the bottom minus the height at the top, and then multiply by mg. Number 4, what's the potential energy of a piano being held 12 meters above the street? mgh. I'll give you a few seconds to calculate that. You get 17,658 joules. Number 5, this is going to be kinetic energy now that we're moving into. When work is done to lift an object vertically, then the work done goes into gravitational potential energy. That's what we've just been studying. However, when work is done to stretch or compress a spring, that energy is called elastic potential energy. And we're going to revisit that later on in the next unit, actually. Kinetic energy is the result of work done not to just move an object, but to speed it up. And I'm not going to go into where this formula comes from as a part of the formal lesson. I might, at the end of this lesson, show you where it comes from. Okay? But in this formula, Ek is the kinetic energy, m is the mass, and v is the speed. And there it is on your formula sheet right here. This is your kinetic energy formula. Again, from Science 10 and junior high science. Take a look at a couple of quick questions. What's the kinetic energy of a 5 kilogram bullet? That would be a heck of a bullet. 5-gram bullet moving at 740 meters per second. Well, it's 1/2 mv squared, which is 1/2 times the mass in kilograms. So I have to divide 5 by 1,000 times the speed. And look how I write this. I put the squared outside of the brackets. And it's a very simple thing, but you'd be surprised how many people forget to square things. That's it. That's all we have to do with this question. And I just prefer to enter 0.5 for a half. And I get 1369 joules. Number 2, 1,500, bless you, a 1,500 kilogram van has 300,000 joules of kinetic energy. What's the speed? So EK is 1/2 mv squared. It's just a matter of putting the numbers in. This is 300,000 equals, this is joules, 1/2 times the mass, which is 1,500 kilograms, times v squared. Here's my thinking, and in Physics 30 we do this calculation a lot. You have to take the energy, multiply it by 2, divide it by the mass, then take the square root. Right? I need to take 300,000. To get rid of that 1/2 on the other side, I multiply by 2. To get rid of the 1,500, I divide by 1,500. I hit equals, and I take the square root of the answer to get 20 meters per second. I think we have one last example. 2? Okay. By what factors does the kinetic energy of an object change if we triple the speed? Do you know, Alex? Right. Excellent. Why? Let me write out the... You explain why. Right. So if kinetic energy is 1/2 mv squared, I could write that as 1/2 m times v times v. So if I triple the speed, what happens is I triple the speed in 2 places in the formula, and I end up multiplying by 3 and by another 3, so the answer is 9 times greater. There are serious assumption problems with question 4 here. But we'll start with the assumption we're going to neglect friction. So I guess what I'm saying is, if there was no friction between a bullet and the air, and I was dumb enough to fire a bullet straight up into the air, how high would it rise? Well, didn't we already calculate this kinetic energy? Wasn't it 1369? So this bullet, when it leaves the ground, here's the ground, this bullet is moving up, and it has 1,369 joules of kinetic energy. It's going to rise to some point up here, and if it's the highest point, it's going to stop. For an instant, right? Like literally an infinitesimally small period of time, it stops and then changes direction. And that means that it has 0 joules of EK at the top. I think you know the answer to this question, but give it some thought. Where did the kinetic energy go? Because I'll tell you what, if we continue watching it, it's going to reach the ground again with that much energy. So the kinetic energy comes back. Where is it at the top? It's gravitational potential energy, which, by the way, there's 0 joules of gravitational potential energy at the bottom. Up here, there must be 1,369 joules of gravitational potential energy. Whoops. Well, that means you can set that equal to mgh and find the height. If we take that 1369 and divide by the mass and also divide by 9.81, we're going to get the speed, the height rather, in meters that it rises to. And it's going to be a ridiculously large number of 29,910 meters, or 29.7 kilometers. it will not rise to that height because friction should not be neglected. But in a perfect situation, that would be the height. Because the bullet is moving so fast, friction with the air is significant. We've talked about this before. If I run down the hallway with my arms out, I feel a little bit of friction. If you were driving a car and it had a sunroof and I stood in the passenger seat, all of a sudden, with both my arms out, I would probably need to go to the hospital if you were traveling fast, right? It would probably tear some muscles. You have some questions dealing with potential energy, some questions dealing with kinetic energy. For the most part, these problems are simply kind of a review of Science 10. Tomorrow we'll move on with this and start looking at, I believe we'll do the work energy theorem tomorrow. In the meantime, get started on these. You have about 20 minutes left in class. I will try to get your stuff marked within the next couple days and back to you.